shown that the square root of 2 is not
I did not. Oh, hi, Mark.
a rational number. We want to spend a few minutes to think about what this means more closely. How can it be? So if you look at your calculator, you're going to get that the square root of 2 equals 1.4141356237 ... So this number, it's bigger than 1 and 4/10, smaller than 1 5/10. It's bigger than 1 and 41 100ths, smaller than 1 and 42 100ths, and so on. It's bigger than 1 and what? 4142 over 10,000. Smaller than 1 and 43 over 10,000. So we can keep doing this literally forever. We're never going to land on a fraction that lands on the square root of 2. On the square root of 2. So no matter how close you get, there's always a gap between them in the rational numbers. You can always get closer, but there's a gap. That's an amazing claim. So let's look a little more at what that means, because where we're going with this is that the real numbers are going to solve that problem. So let's think for a minute. Let me switch pages. I want to dig in a little more now about what it means to say that the square root of 2 is missing from the rational numbers. That there's a gap there, that even though we can get arbitrarily close to the square root of 2, we can get closer and closer and closer to it from either direction, but it's missing somehow, even though you can get as close as you want, but it's missing. I want to look a little more about what that means. To do that, let's start by thinking about, let's just examine a couple of sets here. Okay, so we have two sets on the number line. A is everything to the left of 0. B is everything to the right of 0, including 0. So let's look at this a little bit. A is bounded, which means that there are numbers that are bigger than anything in A. So any number in B, if you have 1, 2, 3, all of these numbers are bigger than anything in A. So 1, 2, 3, those are all boundaries of A. And furthermore, no matter how small, how close you get in B, if you have 1/2, 100th, you can keep getting smaller and smaller. These are all boundaries of A. They're all bigger than everything in A. And even 0 is bigger than everything in A. So 0 is also a boundary of A. So, but notice something else. Even though A is bounded, meaning that all of these numbers are bigger than anything in A, there's no largest element of A. No matter what number you give me in A, I can always find something that's even bigger, right? You say 1, I say 1/2. You say 1/2, I say 1/3, right? You say 1 over 1,000, I'll say 1 over 1,000,000. I can always find a number, whoops, that's 100,000. I can always find a number, oh, all these are negative as well. I can always find a number bigger than the one you gave me and still less than 0. So A does not have a largest number. What about the bounds of A? is there a smallest bound of A? All of these are upper bounds of A, right? 3, 2, 1, 1/2, 100. All of them are upper bounds. Is there a smallest one? And the answer to that is yes, there is. 0 is the smallest upper bound because you can't have an upper bound of A that's smaller than that. If you go even a tiny bit past 0, like 1/1,000,000 minus, then I can find another number in here that's even closer to 0, that's larger than the one you gave me and still less than 0. Or that's larger than that number. So this is not going to be an upper bound. Anything to the left of 0 is no longer an upper bound of A because there are other numbers to the right of it that are still in A. But 0 is the smallest of these upper bounds. And remember here, we're only talking about rationals. We're not talking about real numbers. These are just rationals, that you can always find a rational number that's even closer. And now, interestingly, again, the same thing is true of B. B does have a greatest lower bound. We said all of these are lower bounds of B. -1 is, -1/2, right? There's no element of B that is smaller than 1/2, 1/3, no matter how close you get. There is actually a largest lower bound. Because if I give you a number 0, you cannot find a number bigger than 0 that is still less than everything of B, that is still a boundary of B. Because if you go even a tiny bit over, then I'll be able to find something smaller than that, but still inside B. So 0 is both the greatest lower bound of B and the smallest upper bound of A. The only difference between A and B is that 0 is in B because we have that greater than or equal to 0. But other than that, it's the same boundary for both of them. But with B, the greatest lower bound is an element of B. The least upper bound is not an element of A. Okay, so let's look at one more thing about A and B here. We have that A is everything less than 0, B is everything greater than or equal to 0. If we take the union of A and B, together they cover all of the rational numbers. A is everything up to 0, B is everything greater than or equal to 0. If we change the definition of B slightly, so P is greater than 0, if we change B, so wait, did I do that wrong? Yeah, sorry. P is everything less than 0. B is everything greater than 0. Everything that we talked about regarding the greatest lower bound and the lower upper bound is still true, even though we took 0 out of here. Whoop. Because 0 is still the least upper bound of A. You can get bigger and bigger. There's no largest number in A, but all of them are less than 0. And there's no bound of A that is smaller than 0. 0 is the least upper bound. And at the same time, 0 is the greatest lower bound of B, right? All of these are boundaries of B, but none of them are bigger than 0. It's all the same situation. The only difference is that now B is like A in that its greatest lower bound is not in the set. But what if we take the union of these two sets now? Before, when we took the union, we had all of the rationals. But now, this is obvious, but if we take the union of these two sets, we're not going to get all of the rationals, right? There's one missing. 0. So even though we know these two sets will get infinitely close together, there's still something missing in between them. It's an infinitesimally small slice, but there's something missing. You have to slide 0 in there in order to get all of Q. So in order to get Q, to cover Q, you'd have to say union A, union B, union. You'd have to add 0 in there. So you have all of A, all of B, slide 0 in there, and you get all of Q. So the important point here is that these two sets, they get infinitely close together, but there's still something missing between them. And you can fill that in with a rational number, with 0. Okay, so let's look at a slightly different example now. What if I change the definitions of A and B so that A is all p such that the p squared is less than 2, and then B is all p such that p squared is greater than or equal to 2. So in this case, clearly once again, as above, if we take A union B, we get all of Q. Everything is either in A or in B. What about the lower bounds? Here's 0. Here's 1, 2. There's a number in here somewhere such that if p squared is less than 2, it's going to be over here. And if p squared is greater than 2, it's going to be over here. And we know that this number is the square root of 2, but we know that it's not in the rational numbers. So we know that everything in B is still larger than everything in A. We know that you can always find an A. A does not have a largest element. You can always get closer and closer and closer. And there's some spot where if you go too far, you're going to be in B. That's the same as above when we were looking at 0. And everything in B is an upper bound of A. And no matter how small you get the B, it's still going to be bigger than everything in A. But does A have a smallest upper bound? Does it have a least upper bound? And the answer to that is no. In the rational numbers, no. There is no number here that is the least upper bound. In other words, with A, you can always find an upper bound of A that is smaller than the one that you're looking at. You give me an upper bound of A, I'll be able to find one smaller. You give me a smaller one, I'll be able to find one that's smaller. Forever. There is no least upper bound. When we were looking at 0, if you gave me a least upper bound, I could just say 0, and then that's the end of the game because that's the smallest upper bound. There's nothing smaller. Here, you can't do that. Now, we said that A union B covers the rational numbers. What if we adjust the definition of A and B slightly so that A is still everything, so that A is everything less than 2, squared is less than 2, and B is all p such that p squared is greater than 2. If we take the union of these two, does this equal Q? The answer is yes. Even though this is no longer equal to, we took out this something. We changed it from here to here. Even so, even though neither one of these is greater than or equal, less than or equal, we still have all of Q. We've still covered Q. So up here, all of these combined with all of these is all of Q, even though we know that there's a gap in there. A has upper bounds. A does not have a least upper bound.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.